as modeling a sine function, but only certain parts of it, all right? So what we're going to explore is this concept of a Taylor polynomial, because what this is some aspect of a Taylor polynomial. But if we could actually expand this concept, it is possible that we could actually come up with a polynomial expression that could model the entire sine function, right? And so that's what we're going to be working towards. A little bit of a spoiler. I have 3 terms of this expansion. If I had 4 terms of the expansion, perhaps there would be more of the sine wave covered. If I had 100 terms of the expansion, maybe there would be even more. You know, so maybe more is better. So that's something that we're going to be on the lookout for. All right. So that's kind of the motivation there. And so you'd say, maybe, why? Why would we ever want to do that? Well, I don't know about you, but I think the power rule for finding derivatives and antiderivatives is just wonderful. Like when I learned that, I was like, who said calculus was hard? This is nothing. And then somebody was like, all right, what's the derivative of tangent? And I'm like, crap. And they're like, how about cosecant? And we're like, shut up. Natural log? Why? Let's go back. Let's go back to that other stuff. Well, right now I'm giving you an opportunity to go back. But we got to go forward in order to go back. All right, so I'll show you where these magical things called Taylor polynomials and Taylor series come from. And then I'll show you how we could use them to avoid ever having to work with trig functions, log functions, and things like that ever again. All right. Now, there are some circumstances where you might say, well, I would prefer to work with a trig function. But generally, software, for example, it's all numeric based. You know, like even calculators that say that they're CAS enabled, you know, they're not doing algebra. There's no little dude living in the calculator doing the algebra for it and just spitting out the answer. It's programmed with all the information that it needs to know, but it's all numeric based. All right, so you know what a linear regression is? And there's other types of regressions. So what's really happening is points are generated by finding derivatives, for example, coordinates, and those coordinates are fit to different functions. Those functions are what the calculator perceives to be the derivative of a particular function. Same thing with like Wolfram Alpha and other types of computing software. Right, that's why when you ask it to find the derivative of this, the antiderivative of that, the definite integral over this interval, it does a little thinking, spinning wheel kind of thing. It's crunching the numbers. It's not looking into its vast library. Right? It's doing the math, right? And it's all numeric based, right? So we're going to discover the rule for a Taylor polynomial, and it's a magical ride. So we have this polynomial definition. It's as good a definition as any other. So what we're looking at is an nth degree polynomial in standard form. Now you might look at it and say, well, I thought polynomials were in the form of something times a constant, then something times x, and something times x squared, and something times x cubed, and so on. I say, yeah, that's what this would be if it were expanded out and simplified. These are the standard forms of constant function, linear function, quadratic, cubic, and all the way up to your nth degree equation, all added together. All right, so this gives us the most general form of a polynomial function. So if I wanted a third degree equation, what I would be assuming is that c sub 0, 1, and 2 are all equal to 0, and then c sub 4, 5, 6, 7, 8, all the way up to n are also equal to 0, and this would collapse down to just c sub 3, x minus a to the third. By the way, another spoiler, I'm in a spoilery kind of mood. If you've had a chance to take a look at that tech assignment, this model may seem familiar, somewhat. All right, so if you have had a chance to look at it, maybe, and actually work through it, maybe you're struggling with the latter parts, you know, the parts where you're actually supposed to answer, you know, follow-up questions. Tonight's lesson might actually help you get that part done. All right, so The motivation is the key to everything. So first derivative. So I got to take the derivative of this whole thing. All right. Well, I'm going to start over. Here. It's going to be c sub 1 plus. All right. Now, c's are constants, so c sub o is going to 0. Chain rule, 1 times c sub 1, x minus a to the 0th power. So this x minus a is going away. So that's just c sub 1. Plus 2c sub 2 times x minus a derivative on the inside is just equal to 1, so we don't have to worry about that, because derivative equal to 1 is not going to change the value of the function. All right, 3c sub 3 x minus a to the 2nd plus plus a little typo for somebody. Should be a little plus sign tucked in there in front of the c sub n. All right, anytime, and that's another thing, anytime you see an expansion in your packet, if you see dot, 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 there should be a plus before it and a plus after it. Unless it's a sequence, in which case it should be a comma before it and a comma after it. All right, but there should never be a lack of an operation. All right, next up, if I'm going the distance, n times c sub n times x minus a to the n minus 1. By the way, I'm only writing it underneath because I screwed up the tabbing on this page. All of these f prime, double primes, that should be typeset to the left. So another typo for somebody. Yeah, it should not be in the middle of the page. I don't know what I did. I don't know why that happened.
It isn't for arms.
Oh, that's wonderful. I'll still take it as a typo, because if it's not fixed on here now, it's not going to be fixed here for next semester. So I'll happily take that and give somebody a bonus point. Save me from myself. All right. So, yeah, it's kind of weird. Now, you got to be careful. Well, maybe you don't have to be. I don't know. If you've never taken a stat or probability class, you have nothing to worry about, because you're not going to screw this up. But if you have, this, especially with my handwriting, looks an awful lot like a combination. This is supposed to be a coefficient of 2, then c with a subscript of 2. So big 2, regular size c, little 2. All right. So if you don't know what a combination is, then I guess I'm just not talking. All right. The next one, well, c sub 1, we're going second derivative. C sub 1 is going to cancel away. So we'd be looking at 2c sub 2 plus 6c sub 3 times x minus a plus and then we'd be taking the n minus 1 and multiplying it by the n. So n times n minus 1 c sub n times x minus a to the n minus 2 power. All right, so power by coefficient reduced to power by 1. It's just shaping up to be a fairly nasty expression. Although, maybe not. Because in the next one, 2c sub 2 is going to cancel away, because constant has a derivative of 0. So then we'd be looking at 6c sub 3 plus n times n minus 1 times n minus 2 c sub n times x minus a to the n minus 3. Now we could keep going here, but we actually have enough to start making a generalization. Because what I'm going to do is start evaluating each one of these for when x is equal to a. Which will actually be very easy, because if I'm replacing every x with an a, then every term that has an x minus a in it is going to cancel away. So in each case, it'll be everything except for the first term. So f of a is going to be equal to c sub 0. So that's right back here. F prime of a, c sub 1. F double prime of a, 2c sub 2. F triple prime of a, 6c sub 3. All right. Then we want to start thinking about what those numbers are and where they might have come from. Now, one thing that I am noticing is that, looking at this beefy expansion here, just off on the side, or maybe I'll just do it down here. I'll do it right in this neighborhood. If I were to look for the nth derivative of x, we would keep going many, many more times, right? The next one would be n times n minus 1 times n minus 2 times n minus 3 c sub n x minus a to the n minus 4, and then subsequently n minus 5, n minus 6, n minus 7, and so on. So what we'd be looking at is a set of coefficients n times n minus 1, n minus 2, n minus 3, n minus 4, and so on. We would, in every case, have a c sub n. And then eventually, if we were able to get to the nth term, we would follow that up with an x minus a to the n minus n power. Because I will have taken the nth derivative. If you notice in the first derivative, it was n minus 1. Second derivative is n minus 2. Third derivative, n minus 3. So the nth derivative should be n minus n. Right? So what that tells me is that this piece here, well, that looks an awful lot like the definition of a factorial, multiplying by consecutively lower and lower values as you expand. So that's n factorial. Anything to the 0th power is 1, so that would cancel. So you'd have n factorial times c sub n. That's what my nth derivative would simplify down to. All right, so let's test that out here. So if that's the case, so n here would correspond with the level of the derivative. So what that's telling me is that my coefficient should be n factorial. So the big question would be, this guy here, is this 0 factorial times c sub o? And then we would say for the next one, is that 1 factorial times c sub 1? 2 factorial times c sub 2, and then finally 3 factorial times c sub 3. If these are all true statements, this part here, this isn't a proof, this is a justification. Actually, this is the proof. Right? This part would be just a justification that what we just came up with here isn't completely absurd. In which case, we could conclude finally that this is what we actually think it is. So we'll get to that in a second. But anyway, is 0 factorial equal to 1? Your instincts say no. However, your calculator says yes. Everybody can see that, of course, right? No. You type in 0 factorial in your calculator, it says 1. And for many, many people, you're perfectly fine with that. For many other people, you're like, no, you must prove this to us. Okay, more on that in a second. 1 factorial, that's equal to 1. We go with common sense on that one. 2 factorial, 2 times 1 is 2. 3 factorial, 3 times 2 times 1 is equal to 6. All right, so we're good there. We're good for here, here, and here. But you're looking at this and saying, well, if it's got a 0 in it, 0 times anything is equal to 0. All right, so let's go back to that 0 factorial for a second. I'll just kind of pop it in up here. So we'll go back to our rule. N factorial is equal to n times n minus 1 factorial. All right, so you try something like 0 factorial. Okay, I'll use this rule to prove it. All right, but you get a break. You get a contradiction, you get something that doesn't make sense. The 0 factorial is troublesome enough, but this breaks every kind of conventional rule that exists when it comes to factorials. Specifically the idea that if we're dealing with an expansion of a series, that we're living in the realm of positive integers. So anytime you have a negative result, negative 1 factorial, that's not going to fly. So we're already at a point where we can't use this approach. All right, but maybe you try something like 1 factorial. And the reason I choose that is because if I let n equal 1, what that's going to create is the 0 within the binomial. So on the right-hand side, this is going to simplify down to 1 times 0 factorial, which is the same as 0 factorial. So what we get from this is the idea that 0 factorial and 1 factorial are the same thing. All right? So if you know what 1 factorial is, and we do, 1 factorial is equal to 1, then we now know that that's equivalent to 0 factorial. All right? Most people are fine with, okay, there's a rule, a proof, a reason that he gave in class. It kind of made sense at the time. I don't remember what it is, but my calculator said 0 factorial is 1, so that's what I'm going with. Okay. Honestly, that's how it was for me. Then I became a teacher, and I had to deal with people asking, but why? And I say, well, there's a proof. What's the proof? I'm like, ah, crap. I got to know it, I guess. So I know.
How does 1 factorial equal to 1?
Because if you look at just the general rule behind a factorial, you're starting off with a number and multiplying by every number below it until you get to 1. 1, you're already at 1, so you don't have to multiply it by anything. But anything that's already below 1, you already have an issue, like 0, there's an exception to that. In terms of a practical way of understanding it, just so I can give you a different angle on this that doesn't have to do with a proof, factorials are pretty easy to understand once you conceptualize what the hell they're telling you. They're giving you arrangements, right? If you know anything from high school math related to probability and permutations and combinations and stuff like that, you might remember that permutation and arrangement, they kind of meant the same thing, and combinations were for like groupings, right? But that's probably as far as you got. So and unfortunately that's the reality of it. So what a permutation or a factorial is telling you is the number of ways that you could rearrange a particular a grouping or a set of individuals. All right, so if I took 3 factorial, for example, all I'm really figuring out is the number of different arrangements of those three individuals. And you could play around with, you know, 3 different cards, 3 different objects, 3 different people. You know, if you wanted to line 3 people up, any of the 3 people could occupy the first position in line. Then whoever's in the first position can't be in the second. So any of the 2 remaining people in the second position, and whoever's left over in the third position. 3 times 2 times 1 gives you the 6. That's what a factorial tells us. All right. So the idea of 0 factorial is a really strange one to wrap your brain around, but really it's getting across the idea that if I were to say, I want to determine the number of ways to arrange nothing, how many ways can you do it? You could do it one way, right? And I think of it this way. If I needed to hand you something, so I want you to give me nothing, all right? I can do that in one way. I just did it, all right? What other way could I give you nothing? Like, can I do it like in a fancier way? Like, ultimately, I'm still not giving you anything. So if the idea is for me to exchange something with you, there's only one way I can fail to do that. Now, if I have 3 things, there are 3 ways that I can hand those things to you. All right? So I can hand, 6 ways. I can hand you any of the first 3, and then after that I can start moving things around and trying it in different orders. So, but in terms of just handing over nothing, there's really only one way that could happen. All right? Yeah, I mean, there's applications all over the place for it, but that's a different story for a different day. Anyway, what we get from this is the idea that if I'm really looking to generalize this, it's coming down to the idea that we're looking at n factorial times a. I use C there. Well, okay, so C sub n. And then times a minus a is really what I meant to say. But the a minus a is going to cancel out. They cancel out in every one of these instances, so it would cancel out in this case. So this rule, this expansion, is just a longer way of getting at this idea. All right, so from this, we can solve for C sub n, which would give us the nth derivative of the original function at point A over n factorial. All right, so what we just came up with, if you just go right back to the original polynomial, this is our full-blown expansion. If you go right back to this, what we just came up with is a way in which, if we know what the original function is, so I'm thinking sine function, log function, tangent function, whatever, some funky function, something that's not a polynomial. If I know what its derivative is at a particular point, then I can automatically jump to the most general term of the expansion in one shot. But I'll still show you how to build your way towards that, because it's a pretty interesting process. So this is a typo, because every time I make an edit, I fix something, a new error emerges to take its place. So if f has n derivatives at x equals, that would be a, not c. Some textbooks have c for center, because that's where your polynomial function would be centered. But I just got through deriving the entire formula for you in terms of a, so I don't think it would make sense to turn around and change it to c. And also, I'd have to fix. It's a question of fixing one c or like a bazillion a's and making them c's. All right. So, definition of nth degree Taylor polynomial. You can see it, and you can see the general structure of it. So, every coefficient is taking the form of the derivative, some kind of derivative at a over a factorial, but you still have your x minus a to the nth power. All right. So this is named after Brooke Taylor, who is an English mathematician. That you wanted to research more on that, you could. And then you have Colin Maclaurin, who expanded upon it. And this is not one of those sidekick kind of situations where one person came in after the fact and said, "Oh, I also invented something." Colin Maclaurin did a lot of work with Taylor Polynomials, and so he gets at least as much credit as Taylor. Anyway, typo in addition to that one, the size of the box, if I expanded that, I could have fit mathematician on the same line, so I'll take that also. I think we're at like at least half the class that has full typo bonus. So if you're one of those, I'll say it again, if you're one of those folks who have, submitted a bunch but haven't gotten credit for it, you'll see that you're starting to get credit for it.
How do you check if
Sorry?
How do you check if you have credit for
Blackboard, yeah. So the Maclaurin polynomial is specifically the case where it's centered around a equals 0. All right. So that should, in theory, make things a little easier. However, sometimes it doesn't, at least in the early goings, but it will eventually. You will have to take derivatives, though. And sometimes those derivatives will be funky. In this case, it's not. All right, what we're going to do is find the fifth degree Maclaurin polynomial for f of x equals the sine of x. Now, on the previous page, we did I gave you, I think it was a third degree Maclaurin polynomial. So you'll see that this is just a little bit further. Actually, it might even be the same thing. Let me just look. No, on the previous page, you actually have that graph I showed you was the fifth degree Maclaurin polynomial for the sine of x. So you'll see actually where that formula came from in a second. All right, so what I need are some derivatives. So I have f of x is equal to the sine of x. I'm going to leave a little space. F prime of x cosine of x. Double prime, negative sine of x. Triple prime, negative cosine of x. After that, it's going to recycle because the derivative of cosine in general is negative sine. So negative cosine has a derivative that's equal to positive sine. So we're actually going to recycle for the fourth derivative right on back to whatever we have for the first derivative. So it's kind of like the pattern for the imaginary unit I. When you had I and then I squared, I to the third, it was I, negative 1, negative I, positive 1. It's the same idea. There will be a pattern. And in fact, that happens very, very frequently. So, Maclaurin polynomial is telling me to take the derivative at 0. So sine of 0 is? 0. Cosine of 0? 1. Negative sine of 0? 0. Negative cosine of 0. Negative 1, you said? Yeah. All right. Yeah, unit circle keeps coming back. It's crazy. It's like there's a reason why I keep assessing you on it. So we got that. That's cool. I mean, you can follow the model. I mean, if you do, it's pretty not bad because you're just plugging in. Really, I mean, if you compare what we just came up with to what you have here, it's really only the numerators that you got to worry about. All right? Since the a value is equal to 0, you know, the full-blown Taylor polynomial, you'd have the x minus a. But if a is equal to 0, this collapses down to x squared, x to the n. All right? So it cleans up very, very nicely. So what we're looking at here would be the 5th degree Maclaurin polynomial, p for polynomial function, typical notation. F of 0 was equal to 0. You don't have to write it, but I'm going to write it this one time just to kind of demonstrate. All right. The first derivative was 1, so plus 1x plus the second derivative was 0, so that's going to be 0 over 2 factorial x squared. The next one is negative 1, so negative 1 over 3 factorial x cubed. All right. Now, the shorthand way of writing it has the factorials starting with the second derivative, so you're like, I thought the factorials were all part of this. It's really everywhere. That 1 in front of the x is really 1 over 1 factorial. That 0 is really 0 over 0 factorial. 0 over 1 is 0. So it simplifies down. So in each one of these cases, it's over 0 factorial, over 1 factorial, then 2 factorial. So you have that pattern to rely upon. Right? It's not like the factorials are just coming up out of thin air. Right? Now we're not done because we have to go to the 5th degree here. So we restart the cycle. So plus 0 over 4 factorial x to the 4th plus negative 1 over 5 factorial x to the 5th. Right, so anything that has a 0 coefficient is going to cancel away. And I don't mean the 0 factorial, I mean the 0 on the top. So this is going to simplify down to x minus 1 over 3 factorial x cubed just double checking. Yeah, I knew I messed it up. Should be positive on the 5 factorial. Because I restarted the cycle, I just got my wires crossed. And I'll explain to you how I knew in a second. You know, in the last part of the unit, we learned a lot about different types of series. One of the series that we learned was the alternating series. All right? If the first two terms of an expansion have differing signs, then there's a pretty solid chance that what you're looking at is an alternating series. So when I was about to write this down as minus 1 over 5 factorial, I was like, wait a second, that's pretty rare. So I looked back and I said, that's what happened. I started with 0 and then I was supposed to put a positive 1, I accidentally put a negative 1. So some of these Maclaurin polynomials, Taylor polynomials, are supposed to be alternating series. And if they are, then you can rely upon that piece of information to help you get the expansion. So we now know that our factorials are odd numbers. So if I wanted to go even further, the next one would be minus 1 over 7 factorial x to the 7th, then plus 1 over 9 factorial x to the 9th. I could keep going and going and going with this. And then in doing so, I'll develop a more and more accurate polynomial. And that's really meaningful information.
And that's the exact same question as, or that's the same problem as on the back, because you can just replace the 1 with the x3 and the x5.
Right. You're talking about the previous page?
Yeah.
Yeah, exactly. So, Well, I already typed the equations in, so I'll pull it up on the calculator, but then I'll also show you some other cool things. I really wish there was a way I could do it in real time. It's just so friggin' aggravating. Really just asking us to evaluate some things. So when I'm looking at p sub 5 of 1.2, all I'm going to do in my home screen, because I typed in, I don't know where I want to write it. Well, I typed in the polynomial function in y2. So y2 of 1.2. So again, that's alpha trace. I put the original function in y1. Also alpha trace to get your y1. So instead of actually typing the 1.2 into this, which I don't think would be fun, I'll just hit alpha trace y2 and then open parens, type in the 1.2 and call it a day. You get about 0.93, but I'll write the whole decimal, 932,736. If I do it in the original function, alpha trace y1, type in your 1.2, I'm going to get roughly the same thing. It would round to the same thing, but 932,03908. That's funny. I don't even know what that could possibly be used for. There's like a toolbar that apparently changes your penmanship into squiggles that are shaded in. All right, so in terms of error, just subtract the two. And you're looking at this I think we can round about 6.97, which sounds large until you realize it's times 10 to the negative fourth power. All right, that e negative 4, that's your scientific notation. Now we would do the same thing for 2.1. Now the center, this Maclaurin polynomial, any Maclaurin polynomial centered around a value of 0, right? So 1.2, I mean, I wouldn't say that's close to 0, but 1.2 is closer to 0 than 2.1. So for a 5th degree Maclaurin polynomial, we would expect a more accurate answer for the 1.2 than we would for the 2.1. All right, so alpha trace y2, pop in the 2.1. Do the same thing for the original function. So we're looking at something that's significantly different, I would say. 0.89, I'll round this one about 0.897 because they're far enough apart. And then about 0.863, the difference between the two. About 0.0336. I'll just say 0.34. All right, so infinitesimal difference between the two, a little bit more substantial difference. All right. So how does the error compare? It's larger. If we use it to estimate sine of 2.7, I would expect it to be way off. Now, if I had like a 100th degree polynomial, 2.7 might not be too far off, right? So, but you could test that too. All All right, so the sine of 2.7 ought to be about 0.43. This Maclaurin polynomial is telling us that it's about 0.62. All right, so it's not even close in the world of unit circle trig. All right, so the moral of the story here is that closer you are to the center, the more accurate it's going to be. I feel like I'm answering a tech assignment question right now. And also, if you increase the number of terms in your Maclaurin polynomial, you're going to increase the accuracy. Right on a silver platter is what we call that. And if you missed it, it's on the video, and I will also be saying it about 7 or 8 more times before it's all over, so you'll get it. Find the Taylor polynomial. We'll do this one before the break. Find the Taylor polynomial of degree 6 for f of x equals natural log of x centered at c equals 1. All right. So this is a Taylor polynomial. Let's change that c into an a, just for consistency. That's a nice typo for somebody. And again, just to be clear, there's nothing wrong with having a C there. It's just I'm keeping it consistent with my notes. So if you see a C in a textbook, online resource, whatever, it's still saying the same thing. All right? It's some constant value. And in fact, you might say C is better than A, but I have A mostly here. So I need derivatives. So I'll start with the original function. I'll leave a little space. F prime of x is 1 over x. But since I know I have to take the derivative again, x to the negative first. Leave a little space. F double prime of x is going to be negative x to the negative second. Triple prime. To x to the negative third. And you know what, while I'm at it, let me just get one more in there. Fourth derivative. I wanted to actually go to the fourth derivative at least once with you, just so you can get a little refresher on the notation. It's after the third derivative, you stop using the tick marks to represent primes. So whatever the level of the derivative is, it goes in parentheses, because otherwise it could be confused with a power. Actually, if you wrote f with a power of 4 of x, that really actually does mean y to the 4th power. All right, so it would not necessarily be what you think it is. All right, so now you might look at this and say, I don't see any pattern here, but I'm looking at the coefficients, forgetting about the signs. Well, actually, maybe you don't want to forget about the signs. Positive, negative, it's alternating, so that's something to keep in mind. We also have coefficients, if you're just looking at the absolutes, 1, 1, 2, 6. 0 factorial, 1 factorial, 2 factorial, 3 factorial. Right, so it's still kind of working its way into this whole factorial business. But this time I want to center it around 1. And there's a very simple reason for why we would want to center it around 1. You know, because if you have a choice in the matter, most of the time you want to go with a Maclaurin polynomial, which is always centered around 0. But sometimes you want to go with a generic Taylor polynomial because centering it around 0 is often, for transcendental functions, not the way to go. Because, oh, well, I'll just ask you, what's the natural log of 0? Undefined, yeah. So you got a problem. Actually, you would have a problem for every one of these. So going with the ordinary, the Maclaurin polynomial where it's centered around 0 would be problematic in this case. Centering around 1 is the choice because of that first reason, but also because it's gonna give us a great degree of convenience. Because the natural log of 1 is equal to 0. f prime of 1 would be 1. F double prime of 1 is going to be negative 1. F triple prime of 1 is going to be 2, because all of those x's are going to basically cancel away. All right, so the computations, just for computational reasons, we go with the Taylor polynomial centered at 1. Right? So sometimes you decide on what you want it to be centered around just for the sake of convenience. Like, for example, if I gave you a function, let's say, I'll go back to the sine function, sine of x minus pi. If I centered it around 0, every time I replace x with a 0, I'm going to get a sine of negative pi. Not impossible to figure out, but maybe something you don't want to figure out. But if I center it around a equals pi, then every time I go to evaluate this part of the expression, the x minus a part of it, it's going to give me convenience. It's going to give me a sine of 0. Right? So when we go to tackle the derivative parts of it, you'll be finding the sine or cosine of 0 rather than negative pi, right? So this is a nice case, but what if it were sine of x minus 11 pi over 13? Put a 0 in that, good luck in trying to find an exact value for sine, cosine, negative cosine of 11 pi over 13. So basically, you take whatever's within the trig function, set it equal to 0, and solve. That's what you should center it around, right? Check assignment. So, the polynomial itself. Said degree 6. We learned from the last Taylor polynomial, the Maclaurin polynomial, again, which is a special form of the Taylor polynomial, that sometimes terms can cancel away, right? So, is this enough to get me where I need to go? I don't know. Maybe I'll have to find more derivatives. I do have a discernible pattern here, so I think I'm pretty good in that if I know this is 0 factorial, then 1, 2, 3 factorial, then the next one most likely is 4 factorial. I can test it out by finding another derivative. But at least at the moment, I can get started on writing the polynomial. P sub 6 of x. So our first one was 0 plus 1 over 1 factorial times x minus 1, because it's centered at 1, to the first power. You can put the little power there if you want. Right? In reality, that 0 is 0 over 0 factorial times x minus 1 to the 0th power, because all the other stuff canceled away. All right? The next one would be plus a negative 1 over 2 factorial x minus 1 to the second power. Then we have a 2, so a 2 and a negative 6. So plus 2 over 3 factorial x minus 1 cubed plus negative 6 over 4 factorial times x minus 1 to the 4th, and so on. Now it's just a question of, do I want to rely on the pattern and keep going, or do I want to kind of stop and take stock of the situation, see what's going on? I asked the question so you know the answer. All right, so what I'm going to do is I'm going to clean this up a little bit. This is going to go to 1. Well, so then I might as well just write x minus 1. You know, I'll put the 1 in front. The next one is going to be minus 1 half x minus 1 squared plus 3 factorial is equal to 6. 2 6 is 1/3. So honestly, I think I have it at this point, because if you look at this, the coefficients denominators seem to match the exponent in each case. If this had a denominator, it would be 1. If I wrote the exponent here, it would be 1. So I'm in pretty good shape. I think I can just kind of go for it, but let me just double check. 4 factorials equal to what? 24. What's 6 into 24? What does that simplify down to? 1/4. So minus 1/4 x minus 1 to the 4th. So sometimes taking a sec and really thinking about what's going on can get the job done. We know it's alternating. So the next one's going to be positive 1/5 x minus 1 to the 5th. And then finally 1/6 x minus 1 to the 6th. All right. Under no circumstances whatsoever should you be distributing all this stuff out. All right. Hopefully that's not even something that crossed your mind to begin with. Like you weren't thinking, well, let me just do one of these and stretch out because I know I have to distribute all this out. No, you don't. Hopefully that's not even a consideration. All right. But look for patterns because those patterns really do make a difference. And in all honesty, I mean, at the expense of stealing my own thunder a little bit, we can now get to a point where if I needed to generalize this, I think we would pretty much have it because I would just need to come up with an expression in terms of n that would represent these two values. Right? So if we look at this really, I'm starting off with I have a numerator of 1 in every case. My denominator and my exponent are 1 in each case. All right. So if I wanted to, and eventually I will, I could say 1 over n times x minus 1 to the nth would be an expression that could represent any term of this expansion. However, that would only give us the values themselves. It wouldn't give us the signs. Right? So all I would need to do is multiply this by -1 raised to a particular power. So if you're going through the process of thinking, okay, it's going to be a summation, right? So we're just kind of building it here. I just don't know what the power is. It's going to be a summation, if I want all of them, going from n equals 1 to infinity. We have the 1 over n. We have the x minus 1 to the nth. You expand this out. If I put a 1 here, I get the first term. Or put a 2 here, I get the second term. We're good there. I would just need to figure out what power the -1 would have to be raised to in order to alternate from positive to negative and then back to positive. So what I would say is, okay, try an n. If that doesn't work, add a 1 to it. Right? Because if you think about the alternating series, in general, it was -1 to the nth, or -1 to the n plus 1, or -1 really to the n minus 1, but some deviation from -1 to the n. Right? If I put a 1 in for n here, will this be a positive number or a negative number? -1 to the first power is what? -1. All right? Well, I want it to be +1. All right? So I need to guarantee that it'll be an even number. So I'll just tack a +1 on that. Now if I plug a 1 in for this, 1 plus 1 is 2. -1 to the second power is positive. When I get to the second term, it'll be odd, which will make it negative. When I plug in the 3, that'll make it even, back to positive. And so now I have a rule for the infinite expansion. All right, like I said, I'm stealing my own thunder a little bit because I have a whole lesson on just coming up with this stuff. All right, we're going to explore more of this, but really this is the ultimate goal. because if you think about what we were doing before, you know, with all those different tests, especially the alternating series tests, like we're getting into the idea of being able to approximate a sum with a certain degree of accuracy. I can now, if I wanted to, start thinking about how many terms would I have to go out in order to be accurate to, let's say, 10 units on an XY plane. All right, so it's centered around 1. Maybe I want it to be as accurate as far as from a domain of 1 to 11. I could start thinking about how to make that happen. Maybe 1 to 20. Maybe I want it to be infinite, I don't know. All right, but we can start building our way towards understanding that stuff. But ultimately, the question ends, this particular question, the way it's phrased, and I want to make sure you understand this, this question stops here. All right? That's all it was asking you to do. This is me just foreshadowing what's to come. All right? So I'll even draw a little line there. Very important, because I don't want you thinking that you got to do all this stuff for every question on the test. If a question just said find the 6-degree Taylor polynomial, you're finished at this step, and that's the end of it. This is what's to come. All right, so with that, I'm going to put stars on the next two bad boys. It's weird because the second example, the third example, looks like it would be like the hardest one ever. It's actually the easiest one ever because they give you everything you need to know, right? But I'll let you play around with that. So let's take 5, and then we'll continue on after the break. Third degree Maclaurin polynomial for e to the x. So we need some derivatives. Fortunately, it's e to the x, which has a derivative of e to the x, and a second derivative of e to the x, and a 20th derivative of e to the x, which is just wonderful news. All right, so since it's Maclaurin, I want to do it at 0. So f of 0 is going to be equal to 1. The nth derivative at 0, e to the 0th, also 1. All right, so this is where we start getting into the benefits of using Maclaurin and Taylor polynomials. You can see in part B that it's asking us to find a limit. Right? You could also be asked to find derivatives and antiderivatives, things like that, but more on that in a sec. So the third degree polynomial p of x, p sub 3 of x, 1 plus 1 over 1 factorial x, so just 1 plus x, plus 1 over 2 factorial x squared, plus 1 over 3 factorial x cubed. All right. And you could leave it like that. I mean, there's no reason, there's no requirement to expand out the factorials. The only reason I did it with the natural log question was because in expanding out or simplifying the factorials, it helped me cancel a common factor, which actually helped me develop a rule a little bit easier, right? So, but what we're doing here is we're using our answer to find a limit. Now, e to the x, if I were to plug that in for f of x, I get e to the x minus 1 over 2x, which is indeterminate. I would apply L'Hopital's rule, and after a step or two, I would get the answer. It's not that crazy. But if I use my approximation here as something that can replace f of x, looking at 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed minus 1 all over 2x, you can see that the 1 and negative 1 will cancel, and you're going to be left with x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed over 2x. Simplifies further, because we're still not out of the woods. If you were to replace all the x's with zeros, it would still be indeterminate. You could still apply L'Hopital's rule, but it's kind of defeating the purpose. Every term is divisible by x, so I'll divide an x out of everything. 1 plus 1 over 2 factorial x plus 1 over 3 factorial x squared over 2. And then when we apply the limit, lo and behold, we get 1/2. Which is actually what you would have gotten if you applied L'Hopital's rule, replacing f of x with e to the x. Our first derivative would have been e to the x over 2. Apply the limit, you would have gotten 1/2. All right, so the one thing to keep in mind is that this is not an infinite expansion. So what we're looking at, and this is like it's the cool part, but it's also the part that allows it to work. Maclaurin polynomials are centered around 0, which means that it has its greatest degree of accuracy at 0. So at 0, it's a perfect match. If you're thinking in terms of correlation, like in a stat class, it's got that correlation coefficient, that R value of 1, that perfect fit at that value that it's centered around. All right, it's for each term after in the expansion, it allows it to be more accurate as it radiates away from that center. All right, but at that, you could even think of it as the epicenter. It's the most powerful, like an earthquake. All right, so looking at the limit, you can see we're looking for a limit as x approaches 0, which in a Maclaurin polynomial is perfect because, again, that's what it's centered around. If I were looking for the limit as x approached infinity in this case, this approximation would be terrible, right? Because it's most accurate at 0. This polynomial is going to be nowhere near as accurate for extreme values of x as it is at 0, all right? So if I'm at 20, 50, 100, 100 million, I'm going to lose accuracy. So whatever I come up with as a limit, it may not be even in the same stratosphere as the correct answer. But around the central value of 0, it's going to be very accurate, a perfect match. And since we're approaching 0, that's how you can justify using this approach. All right? So you think of it this way. If I asked you a limit question on the previous page where we did the natural log question, that was centered around 1. If I ask you for the limit as x approached 0, not a reasonable question because you're going to lose some accuracy. I mean, it could be reasonable if you're just looking for an approximate value, but in terms of getting a spot-on exact value, probably not the way to go. But if I ask you for a limit as x approached 1, now we're talking. All right, you'll get a really good, accurate answer in that case. All right, the same thing holds for derivatives and antiderivatives. So if I asked you for the area under the curve, all right, so consider this for a second. If I wanted the area under the curve, e to the x, going from 10 to 20, not a good idea. It's centered around 0, it's most accurate at 0. But if I wanted the area under the curve from -1 to 1, maybe not so bad. All right, I'm going to lose some accuracy, but if I'm just looking for an estimate, I'm going to be in the right neighborhood. If I go from -0.2 to 0.2, very accurate. All right, the closer I get to 0, the more accurate it's going to be. Now, if I want to go from, let's say, -10 to 10 and still use a polynomial, I need more terms. How many more terms? That's a different conversation for a different time. All right. So the next one, I think you're perfectly qualified to handle. Same idea with the next page. Bless you. So now we're actually going to focus specifically on Taylor's series. Isn't that what we've been doing the whole time? No, series, not polynomials. Polynomials will help us get the series, but we want the series expansion and the general term for the series. All right, so we'll start off with e to the 5x centered around a equals 2. All right, so Taylor polynomial, not necessarily centered around 0. All right, this is a general rule, but, you know, and we derived this general rule, and it's a great general rule. Another C is killing me. Yeah, it's a good general rule, and you can rely on it in a lot of cases, but I like to get into how and why it works the way it does. All right, so f of x equals e to the 5x. And for this, I'm gonna work it as we go. So not just derivatives and then evaluation. I'm gonna evaluate each part of it as we go through it. So f of 2, replace x with 2, e to the 10th power. Right, so that's constant, right? So that's good. I mean, we expected it to be constant, but it's kind of a disguised constant because your brain is trying to tell you e to the 10th variable, but e is a number. All right, f prime of x, derivative of exponential functions, keep the function the way it is, multiply by the derivative of whatever the exponent is. So in this case, 5e to the 5x. Evaluate f prime of 2, not f prime of x. So 5e to the 10th power. We're looking to generalize here as much as we can. So let's go out another one and see if we notice a pattern. We have a constant multiplier. Keep the exponential part the way it is. So e to the 5x multiplied by the derivative of the exponent, which is 5, but there's a 5 already there, so 25. All right, so our first coefficient, well, so let me put in the 2. F double prime of 2, 25 e to the 10th power. All right, so our first coefficient was a 1 e to the 10th. The second one, 5 e to the 10th, and then 25 e to the 10th. So another way of expressing each one of those, you could write it as 5 to the 0th, e to the 10th, 5 to the 1st, e to the 10th, 5 to the 2nd, e to the 10th. With the idea being that ultimately, since I'm looking for the nth derivative at 2, I know there's going to be a 5. The power seems to correspond with the level of the derivative. First derivative power of 1, second derivative power of 2. So nth derivative power of n. And in every case, we had an e to the 10th. All right. So in terms of generalizing, that's a big step in the right direction. Because if you look at the general form, now we have to give the first 4 non-zero terms. So ultimately, we still have to do this, but so it ends up being a question of, do you want to do this first and expand it out to equal that? Or do you want to come up with the expansion first and then use your expansion to come up with the rule? There's benefits and drawbacks to either way, all right? So I'll do it the way we were doing it for polynomials. E to the 5x is what we're looking for an equivalent relationship to. So I'm not going to call it p of x. I'm going to call it what it is, e to the 5x. Or you could say f of x, because that's what it's ultimately going to be equal to. All right? Following the model, constant value, so e to the 10th. If you want to write the 5 to the 0th, e to the 10th, that's fine. I'm just going to write e to the 10th. Then we're going to add to that 5 e to the 10th x minus 2, We need 4. So the next one, 5 squared, 25 if you want, e to the 10th, x minus 2 squared. But that coefficient is now over a 2 factorial. And again, it's not a magical appearance of a 2 factorial. Factorials were always there, just you probably don't want to write the 0 factorial and the 1 factorial because they're just going to cancel out anyway. But if you think you're going to forget all the other factors, people do this all the time. They get in the habit of not writing the factorials here, so they never write them. So just build up the muscle memory, write them every time. Over 0 factorial, over 1 factorial. I'll even do it. You get in the habit of writing it, you're less likely to forget to write it. All right? So plus 5 cubed. And at this point, really, I'm not looking at the derivative the list of derivatives I made, because I'm looking at the pattern here. It's 5 cubed. There's an e to the 10th there. The next one's going to be 3 factorial, x minus 2 cubed. And now I have 4 terms, because they didn't say 4th degree, they said 4 terms. All right, the first 4 non-zero terms. 1 term, 2, 3, 4 terms. None of them zero out. So we're good, we have what we need. All right, now what I need to do is come up with my generalization. So plus dot 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 5 to the nth e to the 10th over n factorial. All right. Take note of the quality of these numbers. All right. The power, factorial, well, actually both of these powers and the factorial all match up. So whatever I choose, if I choose to call this n, then these are going to be called n also. All right. Times x minus 2 to the nth power. All right, so that's the general term. Now what I want to do is write it in summation form. All right. Now, one thing to consider. Now, it really doesn't matter. Just generally, the summations are written as starting with n equals 0. All right. So domain-wise, one thing you have to consider is, and this is the departure from what we were doing with the other sequences and series, the numerical ones, is that when you're dealing with polynomials, you can have a 0th degree equation. Your power can be equal to 0. All right? When you're dealing with numbers on a list, if I tell you, give me the 0th number, you're like, what the hell are you talking about? But if I tell you to take the 0th derivative, I'm just telling you to write the original function. All right? So 0 has meaning. But you can define your summation in any way you want, such that the bottom number is like a 1 or 2, a 10, it doesn't make a difference. You just modify your n to accommodate that. But the general rule of thumb is to let the lower bound equal 0 to account for the domain of polynomial functions. All right. So what we're looking at here is the sum going from n equals 0 to infinity, 5 to the nth e to the 10th over n factorial x minus 2 to the nth power. And then what I like to do, and sometimes it's overkill, but I do it anyway, is I just verify the first 2 terms are going to make sense based off of this. So plug in a 0, what happens? Well, that goes away, and that goes away. I'm just left with e to the 10th. Check. Plug in a 1. All right, that becomes 5 to the first, okay. E to the 10th is always going to be there. This goes to x minus 2, and that'll be a 1 factorial, check. All right, 1 or 2 terms, if they check out, then you're in good shape. All right. Now, later on, maybe not tonight, but it's a very quick thing to talk about. You look at this and you say, wow, that's really useful. Like, what can this possibly be useful for? very easy to take a derivative when it comes to something like this. Right? Now, you might look at it and say, it's very easy to take a derivative of e to the 5x, so why do I have to bother with this? Right? This is power rule. Regardless of what you see in the front here, every one of these coefficients, they're just that. They're coefficients. They're numbers. Right? The powers are also numerical. The only thing that's variable is inside the parentheses. So you're looking at something that is in the form of the power rule. So if I wanted to take the derivative of this, power multiplied by coefficient, reduce the power by 1. That's it. So, like, you think about, well, what about the summation? Well, one of the earliest rules you learned about derivatives is that if you're taking the derivative of a sum, you take the derivative a piece at a time, and then you just put it all back together at the end. By ignoring this, you're taking the derivative of a rule that accounts for each element of the sum, each term of the sum. Right? So you're just creating a new rule based off of that sum. The only thing that you might have to consider is what would happen to your bounds. Right? Because if my new exponent is n minus 1, if I plug in a 0 for that, now I have a negative. So is that meaningful? Maybe, maybe not. Depends on the situation. All right. So
graphically, a series is just like dots scattered about, right?
Numerical series, yeah.
Yeah, and then the sum is just the value. Like it doesn't have a graphical representation, right?
Yeah. Well, the sum gives you the heights for each one of those values
Yeah.
as you work your way out from left to right in terms of the numerical system. But for these kind of graphs, what you're looking at, instead of just the numerical values like the positive integers that we're accustomed to from all the other infinite series tests, we also have to account for the fact that x can be part of the set of all real numbers. So that allows for not only the n to vary, but also the x to vary. So n gives us the position within the sequence, but the position in the sequence in this case only translates to the term of the sequence. Each term represents a different function. So the first function is a horizontal line, then you have a linear function, quadratic, cubic, all the way up to an nth degree equation. When you put it all together, the marriage of those functions together give you the exponential function e. Right? So when all is said and done, for Maclaurin and Taylor polynomials, you're not getting disjointed points anymore because of the presence of x, because that could be part of the set of all real numbers. Okay, so that's kind of like the bridge between that numerical stuff we were doing and all the function stuff that you've been learning for years. All right, so 3 special Maclaurin series that you must know. E to the x, sine of x, and cosine of x. Yeah, you must know. It's open notes, so like you should know. It'd be great if you knew. So we know, and so we're kind of beating this to death a little bit, but it's worth it. F of x is equal to e to the x. F of 0 is equal to 1. F prime, well, I won't even go prime. Nth derivative of x is equal to e to the x. Nth derivative at 0 is equal to 1. All right, so if we're just going with Maclaurins here, very easy to come up with. We're looking at e to the x is equal to 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, and so on, with the idea that we're trying to generalize. All right, Maclaurins are easier to come by because you know that the x minus a part of it, instead of having x minus 2, it's going to be x minus 0. So really all I'm worried about is the numerators, because I know my denominators are going to take the form of 0 factorial, 1 factorial, 2 factorial, 3 factorial, and so on. My numerators here are all 1, so that's fine. And we have the x's increasing in degree. All right, so what I just need to do is come up with the nth term of this. Which would be 1 over n factorial x to the nth. All right, because again, just like the last one, just like the last one, the factorial is consistent with the power. All right, so if I'm calling the factorial n factorial, then I can call the power n because those numerical values are the same. All right, so my general rule here would go from n equals 0 to infinity. Once I come up with that nth term, that's what my rule is. I'm just slapping a summation on it. I don't have alternating signs here, so I don't have to worry about a -1 to a power. I just want to just do a quick double check and make sure that if I plug in a 0, I'm going to get a 1. If I plug in a 1, I'm going to get an x, and that happens. If I plug in a 2, I'm going to get a 1 over 2 factorial x squared. All right, so this is the series expansion of e to the x. Y equals e to the x, f of x equals e to the x. All right. Again, what did we do? We took a transcendental function and we made it polynomial. So if I wanted to, I could take the derivative of this. In fact, I'll show you right now. So I'll keep it in, I'll leave the summation off of it for a second. I'll say d dx derivative of 1 over n factorial x to the nth. Multiply your power by your coefficient. And reduce the power by 1. So n over n factorial x to the n minus 1. All right, but if we think about what n factorial is, it's really n times n minus 1 factorial. In which case, the n's would cancel out. So we'd be looking at 1 over n minus 1 factorial x to the n minus 1. All right. Now, if I were to create new bounds for that, because my old bounds aren't going to work, if I plug in a 0 for n, I'm going to get -1 factorial. I'm also going to get -1 as my power. The -1 as a power is not a big deal, but the -1 factorial is going to break the whole thing. All right. So what I would do is I'd adjust my bounds. Instead of starting off at 0, I'll start off at 1. So I have this new expression. All right, now if I start the series expansion of this, plug in a 1, I'm going to get 1 over 0 factorial x to the 0th power, so it's going to be a 1. If I plug in a 2, I'm going to get 1 over 1 factorial, which is 1, x to the 1st. If I plug in a 3, I'm going to get 1 over 2 factorial, x to the 2nd power. If I plug in a 4, I'm going to get 1 over 3 factorial, x to the 3rd power, and so on. What did I just come up with? This expansion, what is it the exact same thing as? No, not Jesus. same as e to the x, right? By plugging in numbers to this new relation, I came up with the exact same expansion as what we started off with. All right, so what we just discovered through admittedly a different technique is that the derivative of e to the x is in fact equal to e to the x. All right, so we did it with a Maclaurin polynomial, but it wasn't really that realization that I was after. It was more so the idea that all we were doing is taking the derivative using a technique that you learned in the earliest part of Calc 1. Power multiplied by coefficient, reduce the power by 1. That's all you're doing. But how do you do that unless you're able to come up with a rule here? All right. Now, we have the little box here to generalize some things, but the question asks, for what values of x does e to the x equal the series that you found? All right, so that's kind of a weird question. But really it's talking about domain. So it's a question of where does your function exist and where does the original function exist? Well, the domain for e to the x has a domain where x belongs to the set of all real numbers. All right, so, because again, we're talking about x here. We're not talking about the n values. N represents the number of terms of the expansion. I'm not talking about that. We're not talking about how many terms do you need to have in order for your expansion to be equivalent to the original function. That's already accounted for by the fact that it's an infinite series. I'm talking about what values of x will work in the original function, domain's all real numbers. In my expansion, the sum of, so from n equals 0 to infinity, of 1 over n factorial x to the nth. Well, fun fact, it's polynomial. All polynomials have domains that belong to the set of all real numbers. All right, so we have consistency here, which means that in every instance for x, I can use this summation, this series expansion, to represent e to the x. All right, so our Maclaurin polynomial is a perfect fit. Maclaurin series is a perfect fit for exponential e. And what that also means, and this is hugely important, I can't emphasize this one enough, is that any transformation of this function will also be true for a set of all real numbers. All right, so if I had something like e to the 5x, e to the 1/2 x, 10e to the 5x, all right, so just think about any way in which you can transform e to the x. You can shift it horizontally, you can shift it vertically, you could dilate it, you can reflect it. It's still going to be true for the set of all real numbers. All right, so if we know this Maclaurin series, then we can come up with everything else. Because really, if you just look at this, compare what we just came up with to this problem here. All right, what we did is we found the derivative, the nth derivative. That changed my numerator from 1 to something else. And then it was centered around a, so we shifted it over. Instead of being x minus 0, it's x minus a. If you know this, you can modify this to come up with that without doing any of the other work. Right? You'll see later on in your packet that there's a table that has the listing of all the popular Maclaurin series. That's a good place to start. Not in terms of memorizing, but in terms of just knowing to reference that whenever you have to come up with a Maclaurin series for something that's not sine, e, or cosine. And by the way, the reason why we focus on sine, e, and cosine is because we're looking for functions that have convenient, not only y values, but also derivatives at 0. All right? So e to the x has a derivative that's e to the x. At 0, it's equal to 1 every time. Beautiful. Sine has a derivative that's cosine, has a second derivative negative sine, so on. It's going to bounce back and forth between -1, 0, and 1. Nice number. Same thing for cosine. You throw in a tangent, now you get a problem. Because tangent at 0, all right, that's fine. There's nothing wrong with that. The tangent of 0 is equal to 0. Derivative of tangent, secant squared. Okay, still not, I mean, it's bad in terms of doing the work, but that's not why it's a problem. Secant is the reciprocal of cosine. So at 0, you're still not in trouble. Second derivative, derivative of secant squared. 2 times secant times tangent. Now it's starting to get a little crazy. Take the derivative of that. Now you have product rule. Take the derivative of that. Are you going to find a discernible pattern? I don't know. Some of the functions you'll have undefined working its way in there, but that's not really the concern. We're looking for convenience in terms of derivatives. E is the most convenient one. Sines and cosines aren't bad. Start moving away from those functions and starts getting a little crazy. Even polynomial functions. All right, but then again, we're using Taylor polynomials to model other types of functions. Why would you use a polynomial to model a polynomial? You already have a polynomial. All right, so I'll put a star on this page because this is sine and cosine. It's basically asking you to do the same thing. We've already looked at sine in terms of the polynomial, but in terms of, you can come up with a series. Now, you flip ahead in the path, so I'll just do the one here and then you'll get the idea. You can manipulate those special cases. You could substitute into the series. You can multiply or divide by a constant and or a variable. Add or subtract two series. Differentiate or integrate a series. We've already kind of addressed that. Or recognize it as a sum of a geometric power series. But let's just focus on the idea of subbing into a series. So, very simple. You start off with the series expansion, or at least this is the way I like to do it. Because you could sub right into the rule. That's not my favorite way of doing it. Maybe you like doing it that way, I don't know. All right, so we know that it's 1 minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, and so on. All right, muscle memory at this point because we've tackled this kind of thing a bunch of times already. All right, you're evaluating a function. Now, if you were to substitute into a function, what do? You replace the variable with a number or another expression. Right? Do the same thing here. I'm going to replace the x, every x, with an x squared. So everywhere I see an x, replace with an x squared. And then simplify. Ultimately, you just want to generalize. You want to come up with a rule that can be used to model this expansion. And this is what I was talking about before in saying that I would show you extensively how to come up with this. You know it's going to have a summation. The bounds are negotiable. We generally want it to start off at 0, so we'll make that assumption. All right. I know that I'm going to have odd denominators. All right. I'm gonna pop in a 1 factorial here. Let me just clean it up a smidge. 1 over 1 factorial. All right. So we want to think about how we could represent an odd number based off of this information. So odd numbers, even numbers. If I have a number, and I'm assuming that I'm working in the set of positive integers, so 1, 2, 3, 4, 5. Forget about 0 for a second. If I take a number and I want to guarantee it's going to be an even number, what can I do to it? I could perform an operation on any number and make it an even number. I can square it, not in every case, but in some cases. Simpler. Not divide. Multiply. Multiply by 2, unless that's what you said, in which case I apologize. Yeah, multiply it by 2. Right? Take a number and double it, guarantee it to be even, right? Yeah, I mean, you try any number. Assuming you're starting with an integer value. I mean, you get into fractions, different story, right? So 2n will give you an even number. Actually, multiply by any even number, and you're guaranteed an even number. But the simplest way to do it is to multiply by 2. Now, if through addition or subtraction, I wanted to get from an even number to an odd number, what could I do? Subtract or add 1. So your choices are 2n minus 1, 2n plus 1. All right. So really what you're doing, in order to guarantee an odd number, is you first guarantee an even number, because you know an odd number is only 1 unit away from an even number. All right. If you start trying to think about other ways to come up with an odd number, your brain's going to start hurting. But if you think, okay, the number 4, it's 1 unit away from 3, it's 1 unit away from 5. I can get to an odd number by taking 1 step away from 4. I can do the same thing with 6, I can do the same thing with 24. All right? 1 unit away in either direction. So I want to guarantee that my denominator is going to be made up consistently of only odd numbers, but specifically such that they start with the very first one has to be a 1, all right? So out of these two possibilities, if I'm assuming my lower bound is 0, if I'm replacing the n with a 0, which one of these expressions is going to give me a 1? 2n plus 1. So we have 2n plus 1 factorial. All right. So you plug in a 0, you get a 1. You plug in a 1, you get a 3. You plug in a 2, you get a 5. You plug in a 3, you get a 7, and so on. So we're good. We got that. All right. We need it to alternate. So that's the next step in the process. So times -1 raised to a power, but my first sign has to be positive. All right. So my first sign has to be positive. So I need this -1 to start off being raised to an even number. So what should it be raised to? Well, n plus 1 would make it raised to an odd number because I'm starting off with 0.
N?
Just n, yeah. Right? Because if I plug in a 0 to start, -1 to the 0th is 1. We're good. Plug in a 1, -1 to the first is a -1. Then a 2, -1 to the second is a +1. Now we have the alternation that we want. All right, so that's the second part of it. Now I need to address the x's. Well, the easy part is just writing the x. Now it's going to be raised to a power. Now, instead of trying to think of a rule that's going to get you 6, 10, 14, and so on, what I would be thinking of is the rule that gets me from my denominator to the exponent. Because in each case, because I doubled the original denominators, the original exponents, the original exponent matched perfectly the denominator. Now the new exponent is twice the value of the denominator. So if I let my denominator be 2n plus 1, then my exponent has to be double that. All right? So 2 times 2n plus 1. So all of that together, I know it's a mess, but all of that together is a rule, and it's Maclaurin. And the way we guarantee it's Maclaurin is that you just have an x. It's not x minus 2, x plus 4, whatever. It's just an x. That makes it Maclaurin. Now, if you want to clean it up further, you can. You could write it as the sum going from n equals 0 to infinity of negative 1 to the nth over 2n plus 1 factorial times x to the 4n plus 2. That's fine, but that's not a better answer. It's a little neater, I guess. This gets the job done. In fact, I like this one better because this tells me the story of how you came up with each term. Like, I can tell just by looking at this that you had a progression. You're like, all right, let me consider my denominators first, then my alternating signs, then my powers. Here it's like, okay, did you use a rule? Did you just guess? I don't know. You copy out the person next to you. Or divine intervention, you know, that's possible. That could happen too. All right. So step 1 on this one, a little recommendation, because you're looking at e to the x plus e to the negative x all over 2. Start off by thinking of this as 1/2 times e to the x plus e to the negative x. All right, so each one of these has a Maclaurin expansion. Find them, add them together. So add the Maclaurins. And then divide by 2 or multiply every coefficient by 1/2. And then see what pattern emerges and try to come up with a rule for that. All right. If you can handle this stuff, then what I teach you on Monday is not gonna pose any difficulty whatsoever.